All right. Welcome to another One Take Wonder, where we get in my Zoom room and talk about simplifying rational functions. I bet you can't wait. Let's share the screen. Yes. All right. So, simplifying rational expressions. I said functions. We'll get there. We're just at expressions right now. You've actually kind of already done this before if you've simplified monomials. The thing to remember here is that you have a very simple cancellation principle, okay? If you have BA over CA, it's the same thing as B times A over C times A, obviously, right? So now you have this common factor, A over A. A over A is the same as 1. Anything over itself is the same as 1. So that leaves you canceling this out with B over C. Okay, so what we can do when we see an expression like this big honking thing over here is, or this big honking thing over here, is we pull out the factors and then cancel the factors they have in common, because those factors technically just simplify to 1. So I kind of did the work on this already. We'll go over it again anyway. 3x minus 9 and 4x minus 12. If you thought that you could just be like, oh, let's turn 9/12 into something, no. Danger, Will Robinson. No, you cannot cancel over a minus sign or a plus sign, right? This is a binomial. You cannot just cut off one part of the binomial and cancel it away. It's not going to work. It's against the laws of math. If you don't believe me, we could plug in some numbers and prove it to you. You have to have numbers that are multiplied to each other in order to cancel out ones, because when they're multiplied to 1, that's when you can cancel it out, right? So we want to not do that. We want to factor this, okay? We're going to factor it so that it becomes something that's multiplied to something else. Well, what do they both have in common? They both have a 3, right? You can pull out a 3, and that leaves you with just x minus 3. Okay, cool. Then we can factor this bottom term. Now you're probably a lot more on board with this. You're like, oh, right, those both have 4 as a factor, so we pull out our 4, and we're left with the binomial term x minus 3. Okay, now look what we've got. 3 and 4 don't cancel, but we have an x minus 3 on the top and the bottom of this expression. But wait, you said you can't cancel it if there's a minus sign. No. I said you can't chop off the ending if it's a plus or a minus sign. However, this entire binomial factor is x minus 3 over x minus 3. You can get rid of that. That whole thing, the brackets show that it's one factor. So get rid of that. It's 1 over itself. It's 1. So it just becomes 3/4. Now let's look at this one. This one really is just simplifying a monomial. There's not even any addition or subtraction signs or binomial factors to mess with us. It just makes us maybe multiply this out first. So that's what I did. I did -3 times 4, which is our -12 here. And then I combined our x terms. I have an x squared and an x to the 5th. Remember, what we do here is we add our exponents, right? There are a total of 7 x's multiplied to each other here, all right? So x to the 7th. So we have -12x to the 7th, and on the bottom, that's the same, 9x to the 6th. Now we can simplify this out, okay? What does that equal? Well, let's see, factors of 12 include, or -12, I guess, include -4 times 3, of course, and factors of 9 are 3 times 3, and then we have x to the 7th and x to the 6th. Well, that means there are 7 of them up here and 6 of them down here. That means 6 of these cancel out almost all of the ones on the top, right? 6 of these get canceled. So what that leaves us with when we cancel, okay, our 3's go away, right? On the bottom, we have 7 minus 6 is 1. This goes away completely because it canceled 6 of these. And this is going to cancel into just a 1, right? This is going to be x to the 1. So it leaves us with a -4 in our numerator and just an x, because it's x to the 1. And then in our denominator, we have only a 3. Okay, so I broke down my whole numbers so that you could see what I'm canceling. Some of you, I'm sure, can do this in your head. And then hopefully this is coming back to you. If it's x to the 7th over x to the 6th, what you've really got is just x. Okay, let's clear and move down to our next set of discussion problems. All right. Oh, we're back. Look at this. State the excluded values. Oh, we're back to excluded values. Okay, so let me do red for my red. Question. Excluded values for each rational expression. So the excluded values are where your vertical asymptote is. If you were going to graph this, it doesn't have an equal sign, so you don't have to graph it. And in the denominator, we always said it's where x is. I know that's an r, but that's okay. It's still a variable in the denominator. So if there's a variable in the denominator, we still need to set it equal to 0 and solve. That's no big deal. We've solved quadratics before by this point in the year. So we've got r squared minus 36 equals 0, right? So now when I've got that, r squared minus 36, notice how this note that says, ooh, special products. We should notice that r squared minus 36 is that special product called a difference of squares. A difference of squares factors into a minus b times a plus b. So in this case, and I'm doing it off to the side again, just because I know this helps some people than just seeing it written out. We know that this factors into r minus 6 times r plus 6. And again, if you forgot that that's a thing, go back and check up on it. A difference of squares. This is a perfect square. It's a difference because it's subtracted, and this is a perfect square. R minus 6, r plus 6. If you FOIL this out, it turns back into that. Okay, equals 0. And now you use the zero property, or the zero product property, or however your teacher calls it, whatever we call it. I just call it the zero property, which means that if one of these is 0, it makes the other one 0. Like if these something times something is equal to 0, that means one of these values of r turned this into a 0 to make the whole thing 0. So in order to do this, we set each section of them equal to 0. We have our first one, r minus 6, and we set it equal to 0. So we have r minus 6 equals 0. Therefore, r equals positive 6. And over here we have r plus 6 equals 0, so r is equal to negative 6. So our two answers are 6 and negative 6. We've just solved this little quadratic here really quickly because it's in the denominator. That means our excluded values are 6 and negative 6, right? If you plug in a 6 or a negative 6 into this r squared, you're going to wind up with a 0 in your denominator, and all right, so excluded values getting a little more complicated, but not that much more complicated. Nothing you haven't seen before. All right, clearing, moving on down. All right, so this is my wall of text that you can read if you pause it or whatever, but we're going to simplify this expression over here. We're going to simplify and then state the excluded values of r. All right, first we're going to factor it, and then we're going to cancel out binomials. So let's get started on this, shall we? All right, I'm going to change back to black. All right, so 2r plus 18. Okay, what can we factor out there? Let's see if this helps us at all. Well, they both have 2, so it would be 2 times r plus 9. Okay, factor the numerator. Let's see if that helps us any. Let's factor our denominator. Ooh, r squared plus 8r minus 9. Maybe it's been a while since we've done this, but you can use this technique now in my classroom. We call this the X games. I've heard it called the diamond in different classrooms, but it's a method of factoring quadratics where you put your terms here and here, and then you find your factors. So in this case, we want it to multiply to negative 9, and we want it to add to positive 8. Okay, and then we think, what goes there? Multiplies to negative 9, adds to positive 8. Ah, I know, it's 9 and negative 1. Nice. Okay, so this factors into, because it has no leading coefficient, we can put it straight into its factor brackets here. This is r minus 1 times r plus 9. Aha! Now we're at this stage. Cancel out stuff. We have an r plus 9 in our numerator and our denominator. Okay, we can't just take out the r, we can't just take out the plus 9. It's in brackets, it's one unit, it's one binomial factor, it's one factor. I know it has bits in it, but it's one factor. So we're going to factor that out. Bye-bye. And we're left with 2 over r minus 1. And that's our simplified expression. Okay, now, like I said, there's a weird thing. Here's the weird thing. We cannot use the simplified form to find the excluded values. Okay, we can't say, oh, the excluded value, it's just 1. Not gonna work. We have canceled out one of those values that would have made this a 0, right? Either r is equal to 1 or r is equal to -9. Either of those values plugged in here is gonna make this whole thing 0, okay? So if you say that 1 is your excluded value, you'd only be half right. It's only one of the excluded values. When you cancel this out, you're canceling out one of the possible excluded values, okay? So as long as you show the excluded value in the answer. Okay, so here we go. Here's the same expression, okay? So you set it equal to 0 on the bottom. Remember, we're just looking for the excluded values, so we don't have to care about our numerator anymore. We're just looking at the bottom. And we can factor it. We already did that. So we have r minus 1 times r plus 9. Okay, we already did the work of factoring that. And now, we set it equal to 0. What are the two numbers that would cause this to be 0? And this, I might be going a little slowly here, but maybe it's worth reviewing. We set each of them equal to 0. So we have r minus 1 equals 0, and we have r plus 9 equals 0, and that means that r is equal to 1 and r is equal to 9, which means that r can, in fact, never actually be equal to 1 or -9. Those little brackets just mean the set of, never equal to those numbers, okay? So you've simplified here, but r can never be equal to these two numbers. Right? Well, let's move on. You guessed it. Getting more confusing. All right, we're going to look out for opposites. Okay. Let's say we're factoring. Okay. And I'm going to choose a good color here so it shows up. I'm going to pick pink. Okay. We have 36 minus t squared and 5t minus 30. When we factor this, and again, it's a difference of squares, we have 6 minus t and 6 plus t. Cool. All right. And down here, when we factor out a 5, we have 5 and t minus 6. Oh, don't you just want to cancel that so badly? But it's not the same thing, right? Subtraction's not commutative. However, there is a way to make it the same, and that's by factoring out a -1. If you factor a -1 out of this little expression here, and I'm going to just do it over here, it turns into this. Let's look at it. We have 6 minus t. If I factor out a -1, all right, -1, well, okay, we have to now think. -1 times what would be 6? Well, -1 times -6 would be 6. And -1 times what would be -t? Well, -1 times +t would be -t. Wait a minute, that's still not the same thing, is it? Yes, it is, because now it's addition. We use the commutative property to say, okay, the -1's on the outside, and I'm just going to move this t to the front, and I'm going to move this -6 to the back, and you have -1 times t minus 6. Okay, it works. And now we have a t minus 6 and a t minus 6, and we can cancel them. Yay! Okay, when we cancel them out, we're left with the -1 gets scooched over here, and we don't actually ever write -1 on the outside, really, do we? So it's just -6 plus t over 5. If you wanted to go ahead and distribute that through, you're welcome to. You're not required to. Okay, so we simplified it. It's simplified. This is the simplified form here. Huzzah. Now we have to find our excluded values. Okay, again, going back to our original. Now, you can back to your factored original. You just want to go back to the version of this that is before you canceled anything. If you've already factored it, keep it factored by all means. 5 times t minus 6. Okay, well, I've sort of talked my way through it here. 5t minus 30 equals 0. We could also just solve it here. Obviously it's not 5, but if you put in a -6 or a +6 here, you'd have a 0 times 0. Boom, you're done. Okay, so t cannot equal 6, and I'm just going to show you that real quick. It's 5. In this case, I just took this down here, 5t minus 30 equals 0. The next step was 5t equals 30, therefore t equals 6. If you do it from this version, you would set that equal to 0, and you just say, oh, okay, well, divide by 5, and then it's just t minus 6 equals 0, and then t equals 6. Okay, either way you want to solve it, it's fine, as long as you don't do it after the fact. Okay, right here, this doesn't look like a rational function. There's no, I mean, it just has a 5 in the denominator. It looks completely like it doesn't look like it's got a variable in the denominator. That's because it's the simplified version. Do not be deceived. It now looks like it is not in the category of rational function, but it is, because it started out over there having a variable. We just ended up canceling it out, but it's still there because it still has excluded values. Okay, so the final answer is over here in this wiggly final answer box right there. All right, and of course your teacher might ask you to distribute the negative. Do it if they say to. All right, your old drawings. Let's move on. All right, don't forget, factor out a -1 if you need it to match. Okay, white space. All right, let's solve some. I did it again. I had it all solved for you. Sorry. Find the zeros of f of x if f of x is this. Cool. So there I went. I factored x squared plus 3x minus 18. I put my c term up here, minus 18. I put my b term down here as plus 3. And what multiplies to 18 and adds to 3? Positive 6 and negative 3. Lucky us, we don't have a leading coefficient. We can leave it alone. We can just go straight into our brackets. And there they are. And then x minus 3. Look, it's on the bottom. Ah, and we can cancel it. Yay! Now we're just left with x plus 6. So if we're looking for the zeros of a function, what does that literally mean? I just realized we simplified this, but we haven't talked about what the zeros of a function are. Zeros are also roots. They're also where the graph crosses 0 on the x-axis. Not y-intercepts, they're the x-intercepts. So when you get to this, it looks extremely simple, doesn't it? It's literally a line. X plus 6 is a line. Like this is, if we were to graph this, I'd not use y, I should probably use f of x because that's what they did. If we were to graph this, it would be f of x equals x plus 6. That's just like a line, but here's the thing. It started out as this big honking monster before we simplified it. It is still a rational function and it will still have an excluded value. Okay, it will have an excluded value, and all of you are doing it in your head right now, hopefully, of positive 3. This will be f of x equals x plus 6, where x cannot equal 3. Okay, that means that when we graph this stinker, it's literally going to be like x plus 6, like 1, 2, 3, 4, 5, 6. It's going to be like a slope of 1, and x plus, it's going to be plus 6, but at 3, right here, it's going to have a hole in that graph, and then otherwise it's just going to be a line. Okay, so all this hot mess graphs out to a line with a hole in it. So there's your hole in a graph that I was talking about in an earlier video where I called asymptotes a hole in the graph kind of wrong. This is an actual hole in the graph. That is sort of off to the side. If they're looking for zeros, they just want to know where this crosses. Okay, so it turns out, and I actually did a pretty good job of graphing this, it would be at 4, 5, 6. Okay, it's going to be at negative 6. Now you wouldn't solve that by graphing it really. You'd just solve it by going, okay, set f of x equal to 0. Set it equal to 0. 0 equals x plus 6. I did it over here in red in very childlike handwriting. And solve. X is equal to negative 6. Your roots, or your zeros, of this function is negative 6. They're not asking for excluded values. I gave them to you because we had just been talking about that, and I thought everyone's going to wonder why we're not talking about that. But this function doesn't ask for excluded values. You actually don't have to find them. You just have to find where it crosses 0. Okay, and it's going to be a pretty wild graph. They didn't ask for that. You're welcome. I told you anyway, just to get the bigger picture around this. All right. Let's try another one. All right. Let's do this one. F of x equals x squared plus 2x minus 15 over x plus 1. Okay. Let us factor this first thing. Of course, the bottom is x plus 1. This thing is going to factor into something. All right, do my little x game that I like so much. It has to multiply to negative 15, and it has to add to 2. Okay, multiplies to negative 15, 5 and 3, and that's a difference of 2. 5 and 3, but then which one, since it's positive 2, then this has to be the negative one because the bigger one has to make, when you add them, makes that bigger. Okay, so now we know, again, no leading coefficient, yay, we have x plus 5 over x minus 3. Wait a minute. There's nothing to cancel here. Ah! Obviously, I knew this was coming. You don't actually have to worry about that. When we're talking about where the function is, where the zeros are, we actually, if you cancel something, that's great. If you can cancel it, go for it. But when you're finding the zeros of the function, you are actually only really worried about the numerator. Okay? You're worried about the numerator because this isn't going to cancel anything out, so it's not going to end up looking like a line. It's going to end up looking like a parabola. Okay? Maybe. I don't know. We'd have to plug it in and see. Now I'm curious. But we know that it has an excluded value there, but they didn't ask us for that. All we know is, well, it can't be 1. 1 isn't one of the roots. We only care about our numerator. All right? So it will cross at see what I did there? X plus 5, I set that one equal to 0. I set that one equal to 0. When you find the zeros of the function, set the numerator equal to 0 and solve. That's it. Solve. Don't panic. Okay? So now we have x is equal to negative 5 and x is equal to 3. Those are the zeros of our function. Okay? So what if you can't cancel? Oh well, solve your numerator. Okay? Let's try this one. We got 2 things here to cancel out, or to factor. If they factor. Let's see if they factor. All right. On this side, we want it to multiply to 8 and add to 6. Well, 4 times 2. No leading coefficient, yay! So we've got x plus 4 times x plus 2 up here. And over here, we have negative 2 and positive 1. Remember, if it's invisible, it's just a 1. So what multiplies to negative 2 but adds to positive 1? Well, maybe we have 2 and negative 1. Okay, again, no leading coefficient, so we can just go x minus 2 times x plus 1, my bad, plus 2 minus 1, there we go, minus 1, and cool, we can actually cancel this x plus 2. Neat. So now our simplified function, of course, is x plus 4 over x minus 1. Now, if I told you, hey, all you have to worry about is the numerator, you might be asking yourself, if all I have to worry about is the numerator, why did you even bother with the denominator? Because sometimes the denominator has something to factor out. If the denominator has something to cancel out, not factor, the denominator has something to cancel out. If the denominator has something that you cancel, then that takes away one of your zeros. That's no longer a 0. right? That's not going to turn into a 0. So you have to check to see if it's going to eliminate one of your possible zeros. In this case, over here, it didn't. This has 2 zeros. Okay, this over here, if none of these had canceled, it would have had 2 zeros, but guess what? One of them canceled. And again, we're not asking for excluded values. That's a sort of a different thought process. We have to see if something cancels, and then we can solve. Okay, now that something is canceled, okay, there's something in the denominator here, but we don't have to care anymore. Now that it's been canceled out, we still just have to focus on our numerator, right? So now we have x plus 4 equals 0. So there it is. Our 0 is -4. There's only 1 0. E-R-O, yeah, 1 0, there we go. 1 0. Okay, just overarching, when you find the zeros of the function, you want to set the numerator equal to 0 and solve. The numerator, to find your roots, your solutions, your zeros, numerator. However, you do still need to check your denominator. You still need to factor it out to see if there's something to cancel. Because if there's something to cancel, it's going to eliminate one of the possible roots. If I had only looked at my numerator, I would think that this had 2 roots. I would think it had -4, and I would think it had -2, but it doesn't. It doesn't have -2. -2 is not a root. All right. In fact, -2 is an excluded value, which is why it can't be a root. So you still do have to factor the bottom and check. But in the end, once you've factored, canceled, or once you've factored and checked and there's nothing to cancel, you only set your numerator. Okay. All right, so I think that winds up our session for today. I could be wrong, but I think, yeah, that's it. Once you see me sending out my my classroom assignments for a textbook that none of you have, yeah, the video is over. All right, I hope you guys liked it, and I will see you in the next video.